relative to resting state. In resting state, permeability to potassium is 100 times greater than sodium. But after stimulation and opening of sodium voltage-gated sodium channels, the permeability to sodium will be increased several thousand times. In this time, the permeability to sodium is highly greater than potassium. So the cell membrane potential going to near the potassium sodium equilibrium potential, a positive number, abruptly going toward the sodium equilibrium potential. In the resting state, potassium conductance is high, sodium conductance is low. We have resting membrane potential. When the cell membrane is stimulated by a local potential, this local potential may be produced by all types of stimuli, chemical, mechanical, and voltage. This period, local potential, may be produced by chemical stimuli, by physical stimuli, or voltage stimuli. A local potential. This local potential, if reached the threshold here minus 50, an action potential will be produced. Fire. Sodium voltage-gated channels have two gates, activation gate and inactivation gate. When the cell membrane potential reaches the threshold, activation gate will be opened, and the channel at this situation is open, increasing permeability to sodium thousands times. The membrane potential abruptly go to the near of sodium equilibrium potential, about plus 30, plus 20, according to the cell and the activity of channels. We say cell depolarized, and this part called depolarization of action potential. The sodium voltage-gated channels abruptly open and abruptly close. They open only in a very, very small time, less than 1 millisecond. Less than 1 millisecond they are open, and then abruptly close. Fast open and fast, close. At this point, the permeability to sodium decreases to resting level because the channels are closed. So the membrane potential shifts to equilibrium potential of potassium. But this phenomenon is very slow. For rapidity, we need another channels, voltage-gated potassium channels. They are open and we have increasing permeability of potassium. This produces a fast repolarization toward the resting membrane potential. And also we have a hyperpolarization because of the more permeability to potassium than the rest. After closing the potassium membrane channels, voltage-gated channels, the potential reaches the resting membrane potential. Here you see the change in conductance of sodium, potassium during an action potential. دقيقاً دقيقاً لا حتما حتما voltage gated sodium channels. Nerve voltage gated sodium channels have two gates. One gate in outer side and one gate in inner side, inside the cell. This gate, outer gate, called activation gate, and the inner gate called inactivation gate. It is not in resting membrane potential, the channel's shape is like that. The activation gate is closed, inactivation gate open in the resting state. Reaching the threshold calls activation gate open, and at the same time inactivation gate slowly go to close the channel. Between these two phenomena, opening of activation gate and closing of inactivation gate, during this time, the channel is open. Abruptly open, abruptly closed. Here, the channel is closed by inactivation gate. Here, the channel is closed by activation gate. In the resting state, the channel is closed by activation gate. In the peak of action potential, the channel also is closed, but by inactivation gate. Between them, the channel is open during depolarization. During repolarization, this shape of channel have a conformational change to this type, from closed by inactivation gate to closed by activation gate. Transform to this in resting membrane potential. Ready for another stimulation. Okay.
Why is its name is activation?
Because it activates channel. You see this channel.
Activation from activity? From activity?
Activity. You see this channel previously. This is activation gate. Open by changing the voltage. Remember,
Yes.
it's open by changing voltage. In a special voltage, this piston move and open the channel. This activation gate. Activation gate. Above the activation gate here, we have a ring of amino acids, special amino acids that have high affinity to the inactivation gate. Above the activation gate here, we have some special amino acids, a ring of special amino acids that have high affinity for this part, inactivation gate. When activation gate is closed in the resting, they don't see each other. There is no effect. But after activation of opening of activation gate by changing voltage, this amino acid can see inactivation gate. Inactivation gate going towards this ring. So close the channel. In threshold is activation gate become open during depolarization. In repolarization, when the potential reaches the amount of threshold, minus 50 for example, the activation gate open, closed, and the inactivation gate released. This shape goes this. And this circle continues. Another important channel we have in action potential is potassium channel. Potassium channel only have one gate. At the threshold, become open, and in reverse mode, close. For threshold, we have 2 points. One, the amount of the voltage, for example, for sodium channel, minus 50. 2, the direction of reaching to the threshold. For sodium channel, during depolarization from negative charge to positive, if we reach the minus 50, the channel become open. In reverse direction, during repolarization, if we reach the threshold, the phenomenon becomes reverse. The channel, the gate closed. The direction of reaching the threshold is important in voltage gated channels. For potassium channels, the threshold is like or similar to the sodium channels, about minus 50. The potassium channel also become open at the same time that sodium channel open. But sodium channel very fastly open and potassium channel slowly open. They are slow. Sodium channels are fast. So opening of channel occur in the peak of action potential. It start to open at the same time by sodium channel. But the full opening occur in the peak of action potential. So the effect of them appear at the peak of action potential. Initiation of repolarization of the cell membrane.
هذا السؤال شو واضح؟
Here you see the action potential and position of two channels in each part. In the resting state, sodium channels is closed by activation gate. Potassium channel, voltage gated potassium channel also closed. In the threshold, sodium channel become open by opening of activation gate. In the peak of action potential, sodium channel are closed by inactivation gate. Potassium channels open. And in the end of action potential, sodium channels closed by activation gate, potassium channels closed. Any question? When an action potential starts, during the action potential, another action potential at this site cannot produce. Only after completing one action potential, another action potential can introduce here.
In the place?
Start here.
The same place?
At the same site. One action potential should be completed, then another action potential can start. This time called refractory period. Refractory period. From starting of action potential to the end, this side of the membrane is in refractory period. Cannot stimulate. Respond to another stimulation. After that, we can start another action potential. Refractory period divided in two types or more. Absolute refractory period and relative refractory period. Absolute refractory period from the beginning to near the end of the action potential. But the relative refractory period from here to here. In absolute refractory period, cell not respond anyway. But in relative refractory period, maybe response to a higher than normal stimuli. For example, in the normal condition, maybe a 20 millivolts local potential produce action potential. But in relative refractory period, you need 15 millivolts for stimulation. The normal stimuli cannot stimulate the cell. Like the example, when action potential produced in the initial zone of the axon. This action potential stimulates the adjacent site and produce another action potential, this action potential, another, to the end, to here. At this site, we don't have the instrument for channels needed for action potential. Here, the conduction is decremental conduction by local potential. In motor neurons, action potential produced in the beginning of axon, here, going to the end. In sensory neurons, action potential produced in the end, going to the center, in reverse direction. What signal produce action potential? In the cell body and its dendrites, millions of synapses are present from other sides of the CNS. Millions of synapses. Each synapse produces a local potential. We have two types of local potential, ISP and ESP, inhibitory synapse and excitatory synapse. Excitatory synapse produce depolarization. Inhibitory synapse produce hyperpolarization. Millions of synapses working here. Some of them excitatory, some of them inhibitory. For example, in some synapse, working of synapse produce activation of sodium channel. Activation of sodium channel produce EPSP. Some other activate chloride channel. Activation of chloride channel produce IPSP or EPSP. Opening of chloride, increasing permeability to chloride. ISP. Some of them are potassium channel. Opening of potassium channel produce ISP. More potassium exit the cell. ISP. Some of them acting on calcium channels, increasing calcium current. Opening of calcium channel produce ESP, excitatory, entering calcium to the cell, positive charge, depolarize the cell. Each local potential produced by each synapse spirit in the cell membrane. They come together. Depolarization added to depolarization, and repolarization, hyperpolarization decrease amount of depolarization. Adding together, and the cell membrane potential, resting membrane of potential of the cell body will be changed to positive amount or to negative amount, depolarized or hyperpolarized. If EPSP more than IPSP, the cell membrane in cell body depolarized, may reach to the threshold of sodium channel. If IPSP more than EPSP, the cell body hyperpolarized. So the probability of production of action potential decrease. More EPSP, more action potential. Less EPSP or more IPSP, less action potential. The cell body works as an integrator. The action potential propagates on the length of the axon to the end. Here, a local potential produced. This local potential causes calcium voltage gated channels here, existing here open, and entering calcium to the cell, produce exocytosis of neurotransmitter. In sensory neurons, the change in environmental physical condition according to the neuron. For example, a neuron sensing the temperature, another neuron sensing the stretch. For example, the pressure sensors have stretch sensitive channels. When you press the site, these channels will be open. Opening of stretch gated channels produce entering of sodium into the cell. Produce a depolarization here, a local EPSP. Excitatory local potential. This excitatory local potential can stimulate sodium channels here and produce action potential. This action potential go to the center. جواب سوال شما مختلف شد. متوسط موضوعی چجوری میاد گفتی؟ روی local potential. The local potential then produce or not the action potential. The velocity of action potential propagation depends on the resistance of the axon. More resistance, less speed. Low resistance, high speed. One important determinant of the resistance of axon is the size of axon, diameter of axon. More diameter, less resistance. For changing the velocity of action potential speed in the axon, we use the size of or diameter. We can change the diameter of axon. But in some situation, for example, in motor neurons that control my muscles, we need velocities that if we try to reach that velocity by the size and diameter of the axon, the nerve that control muscles of my hand maybe have more diameter than my hand. If we try to reach to a speed we need for control of the muscle of our hand, by increasing the diameter of axon, the nerve that enter my hand for control of muscles is bigger than my hand. So we need another mechanism. Allah تبارك وتعالى خلق myelin.
In our last slide, another one. In repolarization, why we just stop in a resting potential and don't do a hyperpolarization?
hyperpolarization occurs because at this time we have both potassium leak channels and potassium voltage gated channels. Permeability to potassium is higher than normal.
Okay.
At resting, we only have potassium leak channels. Here, some potassium channels that produce repolarization are open also.
Okay.
After closing all of them, we reach the resting. Myelin is a lipid structure produced by Schwann cells. You study in detail, inshallah, in histology. Production of myelin produce a huge dielectric around the cell membrane. At this point, there is no permeability at this point to any ion because the myelin covered this part, so any channel can work, cannot work. All the channels cannot work. There is any permeability here. There is no permeability here. Only between two Schwann cells in north of Ranvier. At this point, the membrane is intact and the current will be occurring. At this point, an action potential occurs. This action potential stimulates another node. This node stimulates another node. So the conduction is saltatory. Saltatory.
زياد میشه.
جهشی میشه. saltatory. جهش پرش. جفتش زدن تو عربی میشه. بهترین میشه چی؟ From here, action potential jump to here. And from here jump to another node. So the velocity increased and the energy needed for conduction decreased. And we don't need a large node by myelinization of the nerve. At this site, the capacity of capacitor is very low. More distance between conduit cause increasing capacitance. So capacitance not work, capacitance not work. And at this site, we don't have transmembrane resistance. Only we have intracellular resistance. The decrease in voltage is very low, and the speed of propagation is very high by myelinization of the nerve. Any question?
صوت الفكرة معناها الاشياء شنو الفائدة مالتها؟ كيف
تبقى المسافات تكون أطول.
كما قال الدكتور حد العضلات تشتغل. إذا أردنا وازن بين السرعة والعصب اللي موجود قال انه السرعه تزداد اذا ازداد الدايمتر، كل ما يزداد الدايمتر كل ما تزداد السرعه مال الكوندكشن اللي موجوده داخل النيرف. فاذا نحتاج حتى نوزن السرعه مال عمل العضلات مالتنا فنحتاج على الاقل نيرف قد العضله قد الايد. اوكي؟ فحتى ما نقدر، هذا الشيء ما موجود، فشلون قاعد تصير اصلا العمل اللي قاعد يصير العضلات مالتنا بهذه السرعه وما عندنا هذا الحجم. هذا يجي عمل الماني شيت، الماني شيت هي اللي تنقل الكوندكشن اللي موجود بهذه السرعه. مثل ما تشوفون هنا صارت هنا تغيير، كانت تتغير التشارج. النقل عبر الماني شيت تكون بسرعه أصف ناخذ التشارج ناخذ التشارج
مقاومات این کمه بس برای فیزیک.
بما ان الماني شيت موجود المقاومه من قل، فالانتقال بالتيار راح يصير اسرع واسرع، فيغنينا عن كبر الحجم مال النيرف نفسه. وجود الماني شيت كلش مهم للانتقال بسرعه مال العمل مال الخليه.
During action potential, we have entering of sodium and exiting of potassium. This movement of sodium and potassium change the concentration of intracellular sodium or not. Change the intracellular concentration of potassium in the cell or not.
Yes, change.
During action potential, is there any change in intracellular concentration of sodium or potassium?
No, there's not. Of course there's not. Because of the bomb.
Because
Sodium, potassium bomb.
no, 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 no.
But there's not.
We said yesterday that the amount of ions that move across the cell membrane to produce a huge change, about 100 millivolt, is only 6,000 ions. Is not measurable. So, during action potential, the amount of sodium and potassium in the cell change, but not measurable, not cause any effect. So, if the sodium potassium pump works all the time and replace these ions, sodium potassium works all the time and replace the sodium and potassium, sodium outside and potassium inside. It works. But if we block this pump, also the nerve can work and propagate, transmit millions of action potential after blocking sodium potassium pump. Because the amount of ion moving across the cell during action potential is not high. So after blocking sodium potassium pump, that nerve can conduct millions of action potential. After that, the concentration reach the amount that distort the conduction. Because the amount of movement is very low. It's very important to know. Sodium potassium pump is sensitive to amount of intracellular sodium. A small change in intracellular sodium changes the action of pump progressively. A small change activate the pump. The pump is sensitive to amount of intracellular sodium. Increasing intracellular sodium, increasing activation of, decreasing activation of the pump. وصلنا على محمد وعلى الطيبين الطاهرين.